All right, so we're looking at chapter 2, section 2.3, limits and derivatives. Now we're going to learn how to calculate limits using the limit laws. Now, what are the limit laws? All right, so let's go over this rule here. They say suppose C is a constant and this limit here, so the limit as x approaches a of f of x and the limit as x approaches a of g of x exists. So we assume that these two limits exist, then this is true. The limit as x approaches a of f of x plus g of x is just, you can just split the limits out, all right? And the limit of as x approaches a of f of x minus g of x, again, you can split out the limits. If you have the limit of a constant times a function, you can just take the constant in front of the limit. And if you have the limit of the product of two functions, it becomes the product of the limits of both of those functions. Now look at the division one. The division one, you need to make sure that this bottom limit here is not actually equal to 0. Now, what does it mean that these two limits, they must exist before this apply? It means that if I ask you, for example, to find the limit as x approaches a of, let's choose any of this law, let's say the first law here. Now, if you notice that one of the limits does not exist, so for example, let's say the limit as x approaches a of g of x, that limit does not exist, your conclusion should be that this whole limit that I asked you here, it does not exist. All right, so both of this limit must exist for this to be valid. All right, similarly, if you're doing the product, both of this limit must exist for the limit of the product to actually exist. All right, if one of them does not exist, then your conclusion is that the limit does not exist. All right, when you're doing the division one, always check if the bottom limit here gives you 0. Again, you conclude that that initial limit actually does not exist because you can't divide by 0. All right. Okay. So the first one talks about the sum law. So the limit of a sum is the sum of the limits. And then the second one is just a difference law. The limit of a difference is the difference of the limits. You have the constant multiple law. So the limit of a constant times a function, we say we just take the constant in front of the limit. So it's a constant times the limit of the function. Then we went to the product law that says the limit of a product is the product of the limits. And then we look at quotient, and we say that the bottom piece there cannot be equal to 0. So the limit of a quotient is just the quotient of the limit. All right. We say the bottom piece, the denominator, is not 0. Say for instance, if f of x is close to L and g of x is close to m, it is reasonable to conclude that f of x plus g of x is close to L plus n. All right. So if both limits exist and you're looking for the limit of the sum, then you just need to sum the outputs. All right. So it will just be L plus m. Now let's look at this example here. So they say use the limit laws on the graph of f and g in figure 1 to evaluate the following limits, and then I say if they exist. Right, so limit, you need to be careful. Sometimes it doesn't exist, and don't be scared to say that something does not exist. If it doesn't exist, you say the limit does not exist. All right, now let's start with the first one. We want the limit as x approaches minus 2 of f of x plus 5 times g of x. All right, do you agree the first step will be to, first of all, before you split the limits, so we're looking at the first law, which is a sum law. They say before you split the limit, you must make sure that the limit of the individual function exists, because if one of the limit fails, then the whole thing does not exist. So we'll look at f of x on its own. So what happens when x approaches minus 2? So minus 2 is somewhere there. What happens when x approaches minus 2 of f of x? You notice it, you need to look at it from minus 2 from the left and to the right. And if you look at minus 2 from the left and the right, you actually approaching this number here. So the output there is actually 1. All right. So your output there is 1. And remember, when we talk of limit, it means that we don't care we don't care about what happened at -2 itself, because you can see that f of -2, this is the output up here. All right, it's actually 2. So we don't care about the function evaluated at that x value itself. We're just focusing on what happens when I push -2 from the left and from the right. Right. So in that case, we get 1. So you can see that the limit exists. All right. Then let's look at G now. So for G, when you are pushing -2 from the left and the right, notice it, you get this value there, which is now -1. So whether you're coming from the left or the right, you still end up at -1. So both limit exist. Then you can go ahead to split it now. So you're going to have the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. All right. And all you need to do is to compute the limits and sum the result. You just need to add the result. Now let's go over the solution. You see, the first thing is to first of all see that those two limits exist. Don't do limits blindly. In a test, most of the time, you're going to be very tricked. We're going to trick you because you're going to assume that, oh, if he's asking this limit means actually exists. Sometimes the limit does not exist. So on a rough sheet of paper, make sure you do this test on the side. Make sure that those two limits actually exist. Only then are you allowed to apply law 1, which is the sum law, right? Once I see you writing this, it means I assume that you've done your check and the two limits actually exist. And your next step will just be, after you've seen they exist, you can take the 5 year in front of the, because there's a constant multiple loss. So take the 5 in front of the limit. We've already seen that the limit as x approaches -2 is 1. And for g of x is actually -1. 1 plus 5 times -4, again -4. There you go. So having a number, numerical output, it means that the limit exists, right? Now for the second one, you are supposed to find the limit as x approaches 1 of f of x times g of x, right? So as usual, we test if the limit as x approaches 1 of f of x and g of x separately if they exist. So for f, if I'm approaching 1 from the right, I'm somewhere there, I'm sitting at 2, the output will be 2. So this is from the right. And if I'm approaching from the left, if I'm approaching x equals to 1 from the left, again, you see I'm heading towards that number, the 2. So that limit exists. So I was asking, do you write which law? No, you don't have to write a law, all right? So I assume that you guys know the sum law, the difference law, so just apply it, all right? Let's try for G. For G, the limit as x approaches 1 from the right. Let's see what happens. I'm approaching 1 from the right. Remember, your G function is the blue one. You see there, I'm sitting at -1, and then the limit as I approach 1 from the left. Look at this. This is where the problem comes in. Now, when you are approaching from the left, instead you have -2. There is a problem already. All right. The limit as x approaches 1 of g of x does not exist. Why? Because the limit as x approaches 1 from the right, which is this one here, we're actually sitting at -1. But when we're approaching from the left, we're sitting at -2. So because the limit from the left and the right of -1 is different, it means that the limit as x approaches 1 of g of x does not exist. So in conclusion, you cannot apply the product law. So product law fails here because one of the limit does not exist. So in conclusion, you just say this limit that I asked you does not exist. All right. I hope everyone is happy and that makes sense. If everyone is happy, let's try C. Let's see if they give a nice explanation. All right. So you can see I've already explained the limit as you approach 1 from the left is different from the limit as when you approach 1 from the right. Automatically, this means that the limit as x approaches 1 of g of x does not exist, because the limit from the left and the right must be the same. And because it does not exist, in conclusion, you're going to say that that product, so the limit of the product itself does not exist. All right. So this limit does not exist. Now, how can I make this limit to exist? All right. Is if I now specify, for example, if I say that only focus on the left-hand limit. For example, if I say limit as x approaches 1 from the left of f of x and g of x. All right, if you notice it, for both of them, it is going to exist. And again, if I split it and I say, what is a limit as s approaches 1 from the right of f of x and g of x, you see both limits exist, and I can apply the product rule. But for our original question, this was the original question. The original question was that what's the limit as x approaches 1? I didn't specify if it's from the left or the right. It means you must test from the left and the right, right? And because for g of x, the limit as x approaches 1 does not exist, we conclude that the whole thing does not exist. All right. So, guys, you need to pay attention. The reason I'm saying you need to pay attention because in my assessment, I can give you a limit and I say, if this limit does not exist, what can we do to actually make it to work? You need to prove to me that you understand limit by saying that if we consider left hand limit or right hand limit, which in general we say one-sided limit, it actually works. All right. So I might ask you a question like that. All right. Now for the next one, so someone said, why do we multiply by 2? Okay, you multiply by 2. I'm just going to show you now, because if you consider left hand limits only or right hand limits only, it means you're going to evaluate the limit of f of x separately times the limit of g of x separately. Then you need to multiply that. So if we're looking at 1 from the left, for the f function we have 2, and for g of x from the left we have minus 2. So you see it will be 2 times minus 2. All right. Now if we focus on the limit now from the right, so for f of x from the right you have 2 still, and for g of x from the right you have minus 1, so you have 2 times minus 1. All right. So that is just us trying to make the limit to work. All right. But in a test environment, you have to tell me that our limit does not exist, because looking at the limit as x approaches of g of x, it doesn't exist. So you're going to only do this step here. So this 2 here, you only show me this 2 when I ask a follow-up question that how can we make it to work? Then you need to tell me that one-sided limit makes it to work. All right. So if we only consider it from one side, so either from the left or the right, it actually works. All right, so the last one was the quotient one. So this one, we have the limit as x approaches to f of x divided by g of x. Again, we know that the quotient rule says that you're going to take the limit up and the limit down. All right, it's going to be the limit as x approaches to f divided by the limit as x approaches to g of x. But there is a but. Before you even state the law, or before you write what the law says, you need to check that those limits exist. If any of them does not exist, then you can't proceed. If the bottom one also is 0, you also say that limit does not exist. All right. So for the quotient one, there's so many things you need to test. Both limits must exist, and the limit at the bottom, even if it exists and is 0, you say that this whole limit that I asked you does not exist. So let's see the limit as x approaches 2 from the left and the right of f of x. So 2 is, let me just use a different color. Looks like we've used so many different colors. Let's use blue. So 2 is obviously somewhere here. So approaching f from the left and the right, you see that here we're going to approximate, because left and the right will be somewhere there in the middle. It's probably like 1.5. All right, almost there in the middle. So it exists, and if you look at the g function, if you approach 2 from the left and the right, notice it for this function, you're sitting there, you're sitting on the x-axis, so your output is just 0. It also exists, but now it exists, but it is 0. Very important. It exists, but it is 0. All right, because g of x is 0, and we can't divide by 0. We conclude that this whole limit does not exist, because the quotient law says that provided the limit as x approaches a of g of x is not equal to 0, because we can't divide by 0. Because g of x, the limit for g of x is equal to 0, your conclusion is going to be that it does not exist. All right. So that is the basics of limits. And I hope everyone is happy. So you can see here, we say that The top one is approximately 1.4. In my test, I will not give you stuff you have to approximate. It will be something that you can read off without giving me decimals. And look at G, the bottom one here, 0, which causes a lot of problem. It means that you cannot use law 5. You cannot use the quotient law because you can't divide by 0. So you cannot use the quotient law. All right. If there's no question and everyone is happy, let's keep going. So let's look at some other rules. We'll look at the power law now. For the power law, what does it say? It says that if you have the limit as x approaches a of f of x raised to some power n, so there you're raising your function to some power n, it's the same as evaluating the limit itself and then raise the output of that limit to the power n. All right. So if I say the limit as x approaches a of, let's say, x squared, you can choose to find the limit as x approaches x on its own, and then you square your result. All right. That's just what the power rule says. Now for a constant, the limit as x approaches a of a constant is just the same value. It's just the same constant. Why? Because the constant c is not associated with any x. All right. There's no x term there. So the limit of a constant is just equals to the constant. For example, the limit as x approaches any number a of, let's say 10, is just equals to 10 because 10 is just a constant. All right. Now look at it. The limit as x approaches a of x is equals to a. All right. Meaning that you can just do a direct substitution. All right. Rule number 9. So now if you put f of x equals to x in law 6 and then you use law 8, what do you get? You get the limit as x approaches a of x to the power n is equals to a to the power n. All right. If you remember what the limit as x approaches, the limit of x as x approaches a is just a. So if I say x to the power n, then my output will just be a to the power n. The same apply with root. So n root of x as x approaches a just becomes n root of a. Very important, a needs to be greater than 0. All right, so the assumption is that a is greater than 0. And then for root law, this one is also very, very important, guys. This one here, the rule number 11. The limit as x approaches a of the nth root of a function is the same as the n root of the limit. So I can take the limits inside the root. All right. I can take the limit inside the root provided the limit exists and provided that that limit is actually greater than 0. Very important. The limit needs to exist and it has to be greater than 0 because you can't find the, for example, the even root of a negative value. And the assumption is that n is even, and then we assume that that limit needs to be greater than 0. Direct substitution. Guys, you quickly learn when I give you a limit problem that sometimes a direct substitution works. But because it's so easy and straightforward, we'll try to, you will probably never see that in my test because it's just directly substituting. So what do I mean by direct substitution? For example, if your function is a polynomial or a rational function, and that number a is part of the domain of your function, then you can directly substitute x equals a in your function. So we say that for a direct substitution, if you have limit as x approaches a of f of x, it just becomes f of a. It means everywhere you see x, just substitute a. Straightforward and easy. All right. Now to say in general, we have the following useful fact. If f of x is equal to g of x, so these two functions are the same. When x is not equal to a, therefore the two limits must also be the same. All right. If f of x is the same as g of x, when x is not equal to a, therefore the limit as x approaches a of both f of x and g of x needs to be the same, provided again that the limit exists. All right. Provided that the limit exists. You can't say two limits are the same if one of them does not exist or if both of them does not exist. Now let's look at this example. All right. So example 2, you have the limit as x approaches 5, and then they give you a polynomial. Once you see this, what comes to mind? Direct substitution. Direct substitution means everywhere I see x, I just plug in 5, and boom, I have my output. I'm done. Similarly to b, if you notice it, they say that the restriction is that this number here, so this a here, needs to be in the domain of the function. Then you're allowed to use direct substitution. What's the domain of a polynomial? It's just a set of real numbers. What's the domain of my rational function? The domain of my rational function is such that this bottom piece cannot be equal to 0. And in that case, we're going to say x is not equals to 5/3. But now, if you notice it, a is -2. So it's fine. It means it's part of the domain of this rational function. It means you can go ahead and do direct substitution. And if you do your direct substitution, obviously the first one you just have 39. And the second one, if you plug in -2, you have -1/11. Now keep in mind, this is direct substitution. So when I ask you a limit question, always try and see if you can do a direct substitution. How do you know if it's going to work? Look and check that that number a there is actually in the domain of your function that is given. All right. So the number a must be in the domain of your function. Once that is true, it means that direct substitution is going to work. Now the question is, what happens if direct substitution does not work? We go to method number 2, which is trying to factorize. So for example, 3, if you look at this first one here, a, like I said, for every limit question I ask you, test direct substitution and see. Already you can see that direct substitution is not going to work here. Why? Because look at this bottom piece here. X cannot be equals to 1, because when x is 1, you're trying to divide by 0. So direct substitution fails. The next step is try and see if you can factorize. Yeah, if you treat this function as a difference of squares at the top, notice that one of the factors will cancel with this x minus 1 at the bottom, and you're only left with x plus 1. And your output will just be equals to 1 plus 1, which is equals to 2. So you factorize where you notice that direct substitution does not work. Please, I don't want you guys to be terrible in my test and you just do direct substitution, it doesn't work. You say the limit does not exist. That would be the worst thing in the world, because I can tell you already that I would probably that you have almost a 99.99% probability that the question I'm going to ask you is not a direct substitution question. It means you need to think of the other techniques like factorizing, rationalizing, and so on. All right. I'm just going to try and share the PDF, because for some of you don't understand when I talk of you need to factorize. I'm just going to put up the memo here so that you can see. The solution is already available on Blackboard, guys. So if you go to Blackboard, it's there. So you see there for the first one, all you had to do was to factorize this top piece here. So x squared minus 1, you treat it as difference of squares. So you have x plus 1, x minus 1. Notice these factors cancel out. And therefore, you have the limit as x equals to 1 of just x plus 1, which your output is just equals to 2. All right. So everyone is happy. Then we're going to look at the second one now. Now, for the second one, I give you a piecewise function. So I'm just going to open it quickly. All right, for the second one, I give you a piecewise function, and look at this carefully. If you see a piecewise function, which most of the time or many times with piecewise function, you don't have to panic, all right? Just use the laws of limit. What does the law say? If I say the limit as x approaches a number a, in this case a is 1, so the limit at x approaches g of x, it means that, or it means you need to check what happens when I approach 1 from the left. What output do I get? What happens when I approach 1 from the right? What output do I get? Are those two outputs the same? If the answer is yes, then that is the limit as x approaches 1. We don't care about what happens when x is equals to 1. So what does that mean? It means that for that piecewise function, this second piece is completely useless. You don't need it at all. Because when we talk of limit, we don't care about what happens when x is equals to a itself. All right. So your focus will just be the top function here. Only this top function. That is where your your focus is supposed to be. Now, what happens when you oppose 1 from the left? It's just going to be 2. It will be 1 plus 1. What happens when you oppose 1 from the right? Again, you're going to use the top function. It's t2. Therefore, what is the limit as f opposes 1 of g of x? Your output is just equals to 2. All right. You see, I didn't even make use of this bottom function here because we don't care about the limit when x is actually equals to 1. We don't care about that. We just care about when x is not equals to 1, meaning that it's actually less than 1 or is greater than 1. All right. Now for C, you need to think of rationalizing. All right. When I talk of rationalizing, it means that focus on the function that contains the root sign. All right. So before you even see that it's a rationalizing problem, try and do a direct substitution. Direct substitution doesn't work. Why? Because look at the bottom here. T squared cannot be equal to 0. What does that mean? It means t cannot be equal to 0. So if I actually the limit as t approaches 0, obviously it means direct substitution is not going to help you because you have something divided by 0, which is undefined. All right. So direct substitution first. Obviously, you can apply a second method, which is factorizing, because this is not a polynomial, so there's no factorizing here. So what do? You think of rationalizing. When I talk of rationalizing, what do I mean? I mean you multiply top bottom by the root function, by the conjugate actually of the function that contains the root sign. All right. Some of you, I'm sure you're very happy when you hear the word conjugate because you saw it in complex numbers. In this case, when I talk of the conjugate, I mean that you multiply this function top bottom by the conjugate of this. So where you see plus here, where you see minus is going to be plus actually. So I'll just open the PDF of the memo just so that we are all on the same page. And when you see it in my text, you should be smiling. There we go. So look at C. For C, you see here, direct substitution fails. All right. So don't be quick to say it does not exist because you'll be very surprised you're going to get a 0. All right. So how do you solve this? You multiply top bottom. So first of all, identify the function that contains a root. So you see this whole top piece there. If the root was at the bottom, then we're going to focus on the bottom function. So in this case, we focus on the top function. We multiply top bottom by the conjugate. It means that swap this negative sign to a positive now. You see there. I multiply top bottom with the conjugate. Now, when you do this thing in mathematics, you haven't changed the initial limit. Why? Because these two can still cancel out. All right. So if I multiply a function top bottom by the same thing, then I haven't changed the initial question. And why are we doing that? We're trying to get it to a form where it can actually work. So if you multiply there at the top, you have t squared plus 9 minus 9. You have t squared, and then look here, something interesting happened. T squared cancel with t squared at the bottom. You just left with 1 over root of t squared plus 9 plus 3. And here, direct substitution work. All right, because if t equals to 0, I have root of 9, which is 3 plus 3, which is 6. So it's 1 over 6. You see? So we've implemented rationalizing. All right. So once you identify a rational function, and then you see there's a root that appears at the top or at the bottom, then you need to multiply top bottom by the conjugate. All right. Very, very important. Now, another question is, what happens if there's a root both at the top and at the bottom? Which of them are you going to use as a priority? The priority is the root at the bottom. All right, guys, very, very important. The priority is always the root at the bottom. The same way in complex numbers, when I give a complex number in the rational form, and I say give me in the form a plus bi, you always use that complex number at the bottom. You multiply top bottom by the complex conjugate. It's the same idea. All right. So even for limits, if you have roots appearing at the top at the bottom, focus on the one that is at the bottom. If there's no root at the bottom, use the one that is at the top and then multiply top bottom by the conjugate, and you see it's going to work. All right. Our next question, let's see what the next one is. All right, sorry for the delay. Every time I need to open the PowerPoint slide and scroll all the way to the bottom. So for D, okay, for D, this is just simplifying. So sometimes direct substitution does not work. And then there's no rationalizing here. Now you need to be careful. There's a difference between C and D. For D, there's no rationalizing. You can't rationalize because there's no root. All right. So what do you do here? Direct substitution doesn't work. Just go the extra step of squaring this thing out. So square this thing out. Notice it. 9 will cancel out. You can factor out an h that will cancel with the h at the bottom, and it's going to work. So sometimes when everything doesn't, you seem so lost, you don't know what to do, just simplify. All right, just simplify as much as you can. All right, by simplifying, you're going to notice that things are going to work out. Never assume that, oh, the limit does not exist because direct substitution fails. Think of different strategies. Theorem. All right, now the limit as x approaches a of f of x equals to L, if and only if. Guys, I think I've mentioned this like 50 times already. This limit is true, is equals to L, if and only if the limit from the left gave me L, and the limit from the right also gave me L. All right, your limit from the left and the right must be the same. We call them one-sided limits. Your one-sided limit, it means the limit from the left and the limit from the right, they have to be the same. Only then can you conclude that the limit as x approaches a of your function is actually equal to L. If the limit from the left is different from that from the right, what's your conclusion? The limit does not exist. It does not exist. All right. If any of them is different from the other, then you say it does not exist. Now, let's look at some advanced examples. We want to show that, remember, guys, be careful. And I know some of you are very, very stubborn. You don't read. When I say show that this limit is equal to 0, it means it has to be equal to 0. I'm not asking you, is it equal to 0? I say show that it is equal to 0. It means for in your conclusion, you have to show me that it's actually equal to 0. All right. I've done this many times in tests, and some people argue that it's actually equal to 1 or 2 and so on. If I say show that this equals to this, it means if you don't get to 0 as your output or your answer, it means you are completely wrong. All right. So how do we show that this is equal to 0? Guys, you need to put on your thinking cap. Absolute value, there is a definition for absolute value, right? Absolute value can either be equals to x or it can be equals to minus x, all right? So absolute value x can be equals to x or it can be equals to minus x. When is equals to x? That is if x is greater than or equals to 0. When is equals to minus x? When x is less than 0. There we go. So how do you evaluate limit as x approaches 0? You check from the left. From the left, remember the left means when x is less than 0, we're using that bottom function. And if you notice it, your output is 0 because minus 0 is just equal to 0. What's the limit as x approaches 0 from the right? You're using this top function here. Again, your output is 0. Because the limit from the left is equal to the limit from the right, my conclusion is that the limit as x approaches 0 of absolute value x is equal to 0. There we go. I've proven that is equal to 0. All right, I hope everyone is happy with that. Now for B, I say prove that this limit does not exist. All right, I'm telling you already in advance that the limit does not exist. You need to show me why it does not exist. You need to prove that it does not exist. Again, whenever you see absolute value, what's the first thing that comes to mind? This definition up here. Absolute value of x, it can be equal to x if x is greater or equal to 0. It can be equal to minus if x is less than 0. All right. Let me just jump to the memo, and then we're going to, then I can explain more from there, because if someone wants me to explain again. All right, I hope everyone can see the memo. So if we go to 4a, see what I was telling you. First thing, when you see absolute value, give me the definition. Absolute value of x is equal to x when? If x is greater than or equal to 0. Absolute value of x is equal to minus x when x is less than 0. Right. Remember, x greater than or equal to 0 means x from the right. And x less than 0 means x from the left. All right. So if I now have to compute the limit as x approaches 0 from the right, of absolute value of x, I need to choose which of these two functions to use. Obviously, from the right, we're using x. Absolute value of x is equals to x, so we're going to use x. And if you substitute 0 there, you just get 0. If you evaluate the limit as x approaches 0 from the left now of absolute value of x, you need to choose is going to be now the second function, because this is the criteria. X approaches 0 from the left. X is less than 0. Again, if you substitute 0 there, remember minus 0 is just equals to 0. So your output again is 0. What's the conclusion? The limit is equals to 0. Why? Because the limit from the right is the same as the limit from the left, which is equals to 0. Therefore, in conclusion, that limit is equals to 0. All right. So whenever actually the limit as x approaches a number, it means I will expect you to test from the left and from the right. All right. And then from the last one, not actually the last one, for 4b, all right, I see the student is happy, so it means we can proceed. For 4b, I said that show me that that limit does not exist. So the limit as x approaches 0 of absolute value of x over x, show me that it does not exist. Why it does not exist? Because again, we're using the same definition. We're using this definition for 4a, the definition of the absolute value function x. So the limit as x approaches 0 from the right, it means when I say 0 from the right, everywhere I see absolute value of x, when I come to this definition, I'm going to use the first one there. It's going to be x divided by x. So absolute value of x is replaced with x. X over x is just 1. And then that constant law now applies, that the limit as x approaches a of a constant is just the same constant, all right? Because this 1 here is not associated with any variable x. So in that case, the limit as x approaches 0 from the right of 1 is just equals to 1, all right? Now, if you try it from the left, notice what happened. You need to replace the absolute value function with minus x. Again, we're getting that from this definition up here. And if you do that, x divided by minus x is just minus 1. Limit as x approaches 0 from the left of minus 1 is minus 1. You see there's a difference. The limit from the right gave us 1. The limit from the left gave us minus 1. Because they're different, in conclusion, what do you say? You say the limit does not exist. Why? Because the left and the right, they're different. All right. Once the limit from the left is different from that from the right, your conclusion should be that the limit does not exist. So you've proven that it does not exist. All right. Now let's look at example 5. Again, I just need to scroll to the correct slide quickly before I show it. All right, so example 4c actually. So for 4c, I'm sure most of you guys know how to do this one already. It's a piecewise function. Remember what I said about piecewise function? You just need to use the correct function. So because we're looking for the limit as x approaches 4, we need to test from the left. And you know from the left, we're looking at this one. This is the meaning of the left of 4. It means x is less than 4. So we're going to use this function. What happens if I put 4 in there? I have 8 minus 8, which is 0. So the limit as x approaches 4 from the left is actually equal to 0. Now, what's the limit as x approaches 4 from the right? From the right means x is now greater than 0. It means we're going to use a top function. Square root of 4 minus 4 is 0. You see from the left is the same as from the right. Therefore, what is your output? This limit exists and is equals to 0. There we go. You have your full marks if you can do that. All right. Sure. They say if f of x is less than or equal to g of x. All right. So f of x is smaller than or equal to g of x. When x is near a, except possibly at a, then we say the limits of f and g both exist as x approaches a. Then we say that the limit as x approaches a of f of x must also be smaller than or equals to the limit as x approaches a of g of x. So the first criteria is that f of x is smaller than or equals to g of x, and both limit exist when x is near a but not possibly at a. Therefore, even if I apply limit, the limit for f of x should also be smaller than or equal to that of g of x, right? And we can even go ahead to say that using the idea of theorem 2, we can now do something called squeeze theorem. Squeeze theorem says that I have f of x less than or equals to g of x less than or equals to h of x. All right. If I can compute the limit as x approaches a of f of x and the limit as x approaches a of h of x, now that those two limits, if they're exactly equals to that number L there, so if their outputs are exactly the same, we conclude using squeeze theorem that the limit of the middle function is just equals to L. All right. Let's look at this, guys. How do you know that I'm asking you squeeze theorem? Squeeze theorem, the easiest way to know that the squeeze theorem is you're going to see a function that is bounded. Bounded means if that function lies between a known upper bound and a known lower bound. For example, we know that the sine function is a bounded function. Why? Because the sine function has a maximum value of 1 and a minimum value of -1. So if I say sine of 1 over x, it must be less than or equals to 1, and it must be greater than or equals to -1. All right. That applies for both sine and cos function. They always lie between 1 and -1. Guys, you need to remember this, because once you see limits and you see some sort of trig function, sine and cos, the first thing that to come to mind is I'm testing you squeeze theorem. All right. Now, once you state, so this should be your first step. The sine function lies between 1 and -1. What's the next step? There's an x squared there, right? There's an x squared there. So I need to multiply all through by x squared. Now, if you remember what, x squared will always give you a positive output, all right? Because I'm raising x to some positive, some even power. So it means that my output will always be positive. So multiplying an inequality all through by a positive value, your inequality sign does not change. All right. Now be very careful, because if it was not x squared, let's say it was x cubed, all right, you cannot multiply all through by x cubed because you don't know what the sign is going to be. But we're very confident that x squared is always positive. Then that rule applies that multiply an inequality by a positive number all through does not change the inequality sign. All right. So in that case, I'm going to have on the left hand side -1 times x squared, which just be minus x squared is less than or equals to. In the middle here, I have the original function that was given to us, the f of x function, which is x squared times sine of 1 over x. Remember, I'm doing this because at the end of the day, I'm looking for the limit of this middle function, so this function here in the middle. All right. So you must make sure that you multiply all through and get to this step here. All right. Now, squeeze theorem says that test the limit as x approaches 0 of this, test the limit as x approaches 0 of x squared. If those two limits are the same, then you conclude that the limit of the middle function as well as x approaches 0 is just equals to the same value that you have. So let's test the limit as x approaches 0 of minus x squared is equals to 0. All right, because minus 0 squared is just equals to 0. Let's test this other side. The limit as x approaches 0 of x squared is just 0 squared, which is also 0. Because those two limits are the same, we conclude that the limit of this middle one here, so the limit as x approaches 0 of x squared times sine of 1 over x is also equals to 0. But very important, you need to say by squeeze theorem. All right. If you don't say by squeeze theorem, you're going to see a very big question mark on your paper, because I'm going to ask you, but why is that the case, that this middle limit must also be equal to 0? You need to stay by squeeze theorem, always squeeze theorem. Mention squeeze theorem. All right. Now for B, so B is a special example. So B is actually a very unique example. All right. The reason I'm saying that B is unique is because, yes, it looks like squeeze theorem, but there's a little bit of a problem. Remember, initially I told you that this number here, so you can see here you have an x. X, we don't know if x in this case is going to be positive or is negative. All right. The reason I say that we're not sure, because when you are approaching 0 from the right, you're very sure that x is positive, right? But when you are approaching from the left, there's a problem. X can be negative, because there's that confusion there that we don't know if it's positive or negative. You can't just multiply. If you say cos lie between 1 and -1, and then you try to multiply through by x, you're not sure if you're going to leave the inequality sign the same or you have to change the inequality sign. So what you need to do for B, guys, you need to pay attention. You need to apply the absolute value theorem. So it means that for your first step, after you mention that cos actually lies between 1 and minus 1. So you've said that cos lies between 1 and minus 1. Your next step here, instead of multiplying by x, here you have to multiply by absolute value of x. All right. And then test the limit for absolute value, that is for the left and the right. And then if they give you the same number, then you can conclude that the limit of the middle one is also equals to that output. All right. Let's see if I actually have it written in my memo quickly. There we go. So guys, pay attention for this last example here, because it's an idea that you also need to know when you do maths 2 as well, calculus 2. So it's a very unique example, because I gave you x times cos of power x. We're not sure if x is positive or negative. You need to force the absolute value sign in the place of x. The guy who asked the question, what happens if it's x cubed? It's more or less the same idea here, right? You have to force the absolute value of x cubed, because x cubed can be positive and it can be negative. So to answer this student about what happens when x is a cube, or if it's x cubed, then force absolute value. All right. Now you see, when I put in absolute value, the reason why the inequality sign does not change when I use absolute value, why? Because remember, the absolute value only spits out positive values. All right. Absolute value of minus 2 will definitely be equals to 2. All right. So because I force absolute value, it means that my inequality sign definitely is going to be unchanged, because my output will always be positive, the positive value of x. All right. And if you apply the limits on the left and the right, notice it, you get 0. All right. You have 0, 0 there. Therefore, in conclusion, the limit of this middle one is also going to be 0. All right. And to even make things very interesting, you remember we already did that example where we tested the limit as x approaches absolute value of x on its own, and the conclusion was that it's equals to 0, right? So in conclusion, we can see that if the limit as x approaches 0 of absolute value of x times cos of power by x, if it's equals to 0, then you can confidently say that the limit, therefore the limit as x approaches 0 of x times cos of power by x will also be equals to 0. All right. So the trick there was just to put in the absolute value sign. All right. Is there any question, or is everyone happy up to this point? All right. If everyone is happy, then it means that we just have one slide left. Let me just go to the last slide. And the last slide is just demonstrating or explaining squeeze theorem graphically. All right. Another word for squeeze theory is sandwich theorem. Please, in my test paper, don't write this is true by the sandwich theorem. I understand, because we told you that sometimes called sandwich theorem, but just stick to squeeze theorem. All right. The reason why we mentioning sandwich or pinching theorem here is because we want to explain squeeze theorem graphically. We say that if we can squeeze or we can put G, we can squeeze G in between H and F. You can see there somewhere, this is a G. We're trying to squeeze it to fit in between H and F, like a sandwich. You see where that word sandwich coming. So we're sandwiching G. So G is used, it's actually put in between H and F. As X approaches A from the left and the right, you see that the limit is also true for G. So if you can get the limit for H and the limit for F, if they're the same, therefore your conclusion is actually that the limit for G is also equals to L. All right. And guys, that's basically it. Is there